Check it out. This is my 3D printed pulley gearbox, and I've given it that name because, well, as you can see, it's comprised of pulleys that function in the terms of a gearbox. If you've seen my other videos that commonly feature hydro turbines, you've probably seen that some of them suffer from too little RPM or too little torque, or sometimes the other way around. This gearbox will now step in the middle and solve a lot of those problems. So let's break it down and check out how I made this and the components inside. So on this end, you can actually see there's a bearing in there. It's a 608 bearing, and it's actually held in by this corner brace a little bit. The corner sits right on that bearing, holding it in place. Then there's a shaft collar right there, one on this side as well. This prevents the shaft from pulling out when we have a load, because a lot of these hydro turbines actually commonly have a load applied and it's pulling on them. So we don't want the shaft just to yank out. So then we have a 20-tooth pulley right here, which is connected to our 200-tooth belt. Right here you can see this ear, as we'll call it, our little faceplate that comes up, and it has two holes through it holding a bolt on either side. These have two nuts on either side locking it together. This bolt is actually not tight against there. You can see it's kind of just floating in there. And these nuts are actually just on there to hold the bolt in here. They're locked together, so this way the bolt can spin without actually loosening or moving. This way, when the bolt spins, the nut that is inside of this little bearing holder, or carriage as we'll call it, is allowed to move back and forth, and then that top nut acts to lock that one down as well. So once it's tensioned, you just lock down these 4 separate nuts, and it won't really move around, and it won't loosen up on you. Coming across, we have a 30-tooth pulley, a 36, 60-tooth, and 80-tooth pulley. And this will give us a ratio of about 1.5, a little less than 2, 3, and 4 to 1. So we get a pretty good ratio. This functions the same way. Is here you can see that's just the head of the bolt, which allows us to spin it. I've actually just been able to spin these with my fingers once these locking nuts are loose. So as you can see right here, right now we are on the 1.5, and this is our output shaft currently. So if we use this as our input shaft where the hydro turbine would connect, right now we would get an increase of 1.5. So if this spins at 10 RPM, we'd get 15 on this side. So right now it will not increase our torque. It actually requires more torque to spin this to get the higher RPM. But we have plenty of torque and just suffer from RPM. So in our current hydro turbine testing, this should be a perfect scenario. I'm guessing we'll probably find more luck with the 36 tooth, but who knows? We have all these to play with, and it is fully adjustable to meet all of these sizes that are currently on here. You can get a little bit bigger and a little bit shorter. I just didn't see a need because this gives us a pretty good range and ratio. So let's get it connected to the drill and see what kind of testing and output we can get. It should, in theory, make more power or more RPM with each test. So now that we've gone through the parts, let's get it connected and see what kind of power we can output. Right here you can see, in this case, our input shaft is going to be the one with all the pulleys on it. So as we change the ratio, the RPM will increase on our output shaft. If you've been around this channel for a while, I have some exciting news for you because this has been a top comment for a very long time. This is our 250 watt DC brushed motor. I've used it in almost every single one of my tests other than I think 3 videos, which you should check those out. That would be the waterfall turbine, tow turbine, and power on a stick. I'll link those in the description below. But this is the motor we've used on almost every single other test. It's been around the channel. I do have 2 of them, but they've been around for a long time. They work pretty well. They generate a decent bit of power with moderate RPM. So now that I've had a lot of requests for this for a very long time, I've stepped up the game and I've purchased a brushless motor. It's a little bit smaller, but it is technically rated for more power. Let me move this for a second. This is a Flipski 6374 140 kV motor. It is a 3-phase motor, but we have gone ahead and soldered it up to our bridge rectifier. So now we have a DC output, a 12, maybe not 12, but a DC output. This motor is technically rated for, I think, 3600 watts. And if you're wondering what this big red shroud is I probably will still test it, but my idea with the tow turbine was I was going to be able to just connect it right here, hold it, and go test. But it seemed like the RPM was going to be too low because the 140 kV rating actually means that you need 140 RPM for each volt. So given the past testing, I figured this RPM would be a little low, and I wanted to have a way to step it up. So before going out there and testing, I decided to come up with this little design, and that's kind of where we're at in making this video. I decided to make a separate video because it's pretty simple when you break it down, but it is a kind of a complex design. So I wanted to make a separate video and showcase this, but I also wanted to elaborate on this new motor. Because if everyone's used to this one, well, it is a surprise, and it will be featured in new videos. And if you want to see it used in the Pelton turbine or any of my other videos, or a video comparing the two motors, let me know. I'd be more than glad to make one. But because we are testing the ratio and ratios only, keeping the same motor will be fine for this test, regardless of which one it is. So for it, we're going to test the new one because why not? I'm pretty excited. I think it'll be a good test. So let's get it all connected. Let's see how well this quick connect coupling stays together. It's actually a flexible mount, but as soon as you flex it, it just falls off. So let's see how well it stays on. This is the 30-tooth pulley. Oh. I'll be honest, I was not expecting 36 watts on first test. Okay, well, I guess I'm going to get the other heaters and I'm going to swap it over to the 36-tooth pulley. I might not have enough heaters for this, but we'll get to that. All right, we've now got the 36-tooth hooked up, so let's see how much power it makes. That sounds good. Did that say 60? Huh. Well, this is the making of a good video because 60, I believe, even on a drill, would still be a power record. And we're on the second test. At a point, I do believe the torque required on the input shaft will probably overpower this drill, like when we get to the 80 tooth, but I don't know. I've been wrong before, and I hope I'm wrong right now because we just set a record even on a drill. So once this gets connected, it's looking pretty good. All right, we've now connected it to the 60-tooth pulley. I've also gone ahead and replaced this shaft coupling right here. It was that flexible one right here, as they call it, but it separates in the middle, which makes it kind of annoying because it just pulls apart, especially if it's flexing at all. So it's now a rigid shaft adapter, and we now have this nice padding, which 2 for 1 right there. So let's see how it does, and it should make a little bit more power than our last one, as long as the torque value or torque required isn't too high. So let's see how it does. It's pretty good. Oh, maybe I might be able to get all of this on there. Oh, there we go. Yeah, so it is actually, it's requiring a little bit more torque, but what I'm doing is I'm just slowly laying into it. So I'll see if I can get the RPM up there. I'm not sure if I'll be able to actually get full throttle on this thing. So let's see how it does without getting our wire sucked into the motor. Oh, the camera's about to fall off the table. That would be unfortunate. So it just gets really rough, and you can see it's because we're requiring too much torque that it actually can't spin. So I think that's probably because we're not going to get much better than that last test, because as we step up to this next pulley, the power is actually just going to go down because we require more. Even if we drop into that second, the first power level on the drill with the 80 tooth pulley, it's still only going to be 4 to 1, which is barely higher than just connecting the drill to it directly. So the best test in this case scenario was actually the 36, but when we're testing in the real world where it's not a drill supplying all the torque, where it's actually the water, which has a lot more torque in theory, it should have no problem spinning these bigger pulleys, thus producing way more output. But 60 watts, even on a bench test, is, I believe, the highest number we've ever seen. So I hope you guys like this little bench test. If you want to see a comparison of this motor on other things, or if you guys have any suggestions or other motors you guys want to see tested, let me know in the comments below. So as always, thanks for tuning in, and I will see you guys in the next one.